Okay, hello everyone. Welcome to the Combinatorics session of ICM 2022. The next speaker is Asaf Shapira from Tel Aviv University. He'll talk about global versus local combinatorics. The talk is pre-recorded, but Asaf is here to say hello just before we start seeing his recorded lecture. So Asaf, please.
Hello everyone. Welcome to the... Hi everyone. Thanks Ehud for this introduction. And I hope everybody will enjoy my pre-recorded lecture. The talk is pre-recorded, but the stuff is here to say hello just before we start seeing it. Okay, so let me start sharing my screen. So the topic of this lecture is going to be problems in extremal combinatorics. So what is this subject all about? So in extremal combinatorics, we ask how large or small or sparse or dense can a discrete structure be, assuming it satisfies some predetermined property. So besides the intrinsic interest in the problems in this area, it has applications in many other areas of mathematics, such as theoretical computer science, additive number theory, discrete geometry, coding theory, group theory, etc., just to name a few. So, but in this lecture, we'll mainly discuss problems related to graphs and three graphs. So a graph, just a reminder, is a set of points, which we call vertices, that have edges that are just subsets of size 2. And so this is, for example, a triangle in a graph. And we will also talk about three graphs where, again, we have a set of vertices, but now the edges, instead of each edge containing 2 vertices, each edge contains 3 vertices. That's why it's called a 3 graph, and we can describe a 4 graph and 5 graph, etc. We will call this 3 graph a 6-3 configuration because it has 6 vertices and 3 edges. So throughout the talk, we will use n to denote the number of vertices of the graph or the 3 graph. And all the problems we will discuss are of asymptotic nature, so we will assume that number of vertices n tends to infinity. So the first problem we will consider is related to this VE configuration. So let's just define them again. So a VE configuration in a 3 graph is a set of V vertices that contains at least E edges. So it's a relatively dense subset of the 3 graph. And one of the central open problems in extremal combinatorics is the Brown-Erdős-Sós conjecture from the early 70s. And it says that you fix a number of edges E, so this is like a small integer. And the conjecture is that if a 3 graph has no E plus 3 E configuration, meaning E plus 3 vertices with at least E edges on them, then this graph is sparse, meaning it contains little O of n square edges, where little O of n square meaning a quantity that is asymptotically less than n squared. In other words, just to the converse is that if a 3 graph is globally dense, meaning it contains a quadratic number of edges, then for every fixed E, we should be able to find an E plus 3 E configuration. Again, it's E plus 3 vertices with at least E edges on them. And a famous theorem of Rouge and Semeredy is that the Brown-Erdős-Sós holds for 3 edges. And this is called, for obvious reason, the 6-3 theorem. And to prove this theorem, one needs the removal lemma, which is the next important problem we will consider. So to state the removal lemma, we need a definition that will be used many times in this talk. So we say that the graph on n vertices is epsilon far from some fixed property P if one needs to add or delete at least epsilon n square edges to make it satisfy the property. Meaning that because a graph has potentially n square edges, what it means is that we should modify a positive proportion of the graph's representation to make it satisfy the property. And what the triangle removal lemma states is that if a graph is epsilon far from being triangle free, then this graph contains a positive proportion of all possible triangles. Now observe that the converse statement is trivial, meaning that if a graph has many triangles, then trivially you should modify many edges in order to destroy all the triangles, simply because removing an edge destroys at most n triangles. Okay, so the main thing here is the forward implication. And observe that if a graph is epsilon far from being triangle free, then it means that if you randomly select 1 over delta of epsilon vertices, then this sample of vertices contains a triangle with high probability. Meaning that there is a constant time algorithm, if assuming the graph is globally far from being triangle free, it's very easy to detect this locally by sampling a constant number of vertices. And indeed, you just sample 1 over delta of epsilon many triples and you check if any of them is a triangle. Of course, if the graph is triangle free, none of these triples is going to be a triangle. And if it's epsilon far, by the removal lemma, a sample of size 1 over delta will catch one of these triangles with positive property. And of course, it's natural to ask for which other graph properties there is such magical constant time algorithm. We'll get to this later. But to prove the removal lemma, we need the regularity lemma, which is our third guiding problem. So to state the regularity lemma, we need to say what does it mean for a bipartite graph to be epsilon regular. So a bipartite graph is just a graph whose edges connect two vertex sets of size n. And it's epsilon regular if no matter which subsets of size epsilon n you pick on each side, so here is two choices, the density between the two subsets is very close to the density between the entire graph. Okay, so it's very simple definition. You may wonder, is it even useful? So now let's say that a partition of the vertex set of a graph into k sets, v1 up to vk, is epsilon regular if almost all pairs of bipartite graph between vi and vj are epsilon regular. Okay, so you can ask at this point, is this notion even useful? And if it's useful, is it true that every graph has such a partition? Okay, so, and what the regularity lemma of Semeredi states is that for every positive epsilon, there is an integer m of epsilon, such that every graph, no matter how large it is, contains an epsilon regular partition. And as you might guess, this statement is useful also for many applications. For example, we can use it to prove the removal lemma, as we'll see later. And of course, at this place, you can ask, are there other variants of this lemma? Is there such a lemma for 3 graphs? What can we say about m of epsilon? We'll address all these questions. Okay, so the first set of results we want to discuss is about the Brown-Erdős-Sós conjecture. So it will be convenient to define the following function, fnve. This is the largest number of edges that a 3 graph on n vertices can contain if it has no VE configuration. So just to recap, the Brown-Erdős-Sós is just a statement that fn e plus 3 comma e is little o of n squared. Okay, so the maximum number of edges in a 3 graph without an e plus 3 comma e configuration is little o of n squared. And let's also denote by rkn the size of the largest subset of the first n integers without a k-term arithmetic progression. And the Rouja-Semeredi theorem that I've stated earlier is just that fn63 is little o of n squared. This is what I've said before. But they also prove that fn63 is at least n times r3n. So they used a very clever graph construction based on subsets of integers without a 3-term arithmetic progression in order to prove a lower bound, for meaning that to find a 3 graph with a large number of edges and no 6-3 configuration. And let me just mention that the first inequality is Beret's construction that says that R3n is at least n to the 1 minus little o of 1. So here, a very surprising application of this theorem of Rouja and Semeredi, if you look at these two inequalities, is R3n is little o of n, which is of course a famous theorem of Roth. Now, unfortunately, already the next case of the Brown-Erdős-Sós conjecture, meaning the case of 4 edges on 7 vertices, which is called the 7-4 problem for obvious reason, is open. And it's probably open for good reason because it implies the notoriously difficult Semeredi theorem for 4-term arithmetic progression. So with this state of affairs, it's natural to consider approximate version of the Brown-Erdős-Sós conjecture, which I'm stating again. So it says that if you forbid E edges spanned by E plus 3 vertices, then the 3 graph contains at most little o of n square edges. So Sarkozy and Selko used repeated applications of the triangle removal lemma in order to prove an approximate version, meaning that if you forbid E edges spanned by E plus log E vertices, then you get little o of n squared. And to do this, they used the process in which they, at each state, doubled the size of the previously constructed configuration, where at each step they lost a single vertex in the difference between the number of vertices and edges, and this is why you get this log E. And a few years ago, Sholimoshi and Sholimoshi managed to improve one case of this Sarkozy-Selko theorem. Meaning for 10 edges, they improved the number of vertices from 15 to 14. This seems like a negligible improvement, perhaps, but it requires a very sophisticated idea in which they use the three-graph removal lemma in order to once triple instead of double a 6-3 configuration. And in a recent joint work with Conlon, Gish-Boliner, and Vanzov, we managed to obtain the first asymptotic improvement of the Sarkozy-Selko theory we replaced the log E by log E over log E. And to do this, we had to devise a somewhat complicated process to generate this configuration, where instead of only doubling them, we double, triple, quadruple, etc. And to do this, we had to use the R-graph removal lemma, which will be mentioned later many times. Okay, so let me now consider the other direction of the Brown-Erdős-Sós conjecture. So we know that by the Rusha-Semeredi theorem that an upper bound and a lower bound, and given the difficulty of proving upper bound, it's natural to conjecture, and this is a folklore conjecture, that not only we have this upper bound, but we have a nearly matching lower bound. Now, so we have this, the Rusha-Semeredi proved the lower bound for 3 edges, and for 4 edges and 5 edges. This follows immediately from the 6-3 theorem, simply because each of these configurations must contain this configuration. But already the next case, the case of 6 edges and 9 vertices, is open. And it seems like the heart of the matter is to consider the 3x3 grid. So let me use G to denote the 3 graph that has 9 vertices and 6 edges, that the 6 edges are organized as the 3x3 grid. And let me also define the 3 graph to be linear if every pair of vertices in it has at most 1 edge. And observe that a linear 3 graph has at most n over 2 divided by 3 edges. And in this case, it's called the Steiner triple system. So Furedi and Rusinko conjectured that there is a linear G-free 3 graph with almost the maximum number of edges, almost as a Steiner triple system. But on the other hand, Elekesh, a few years earlier, conjectured more or less the opposite, is that if a 3 graph doesn't contain the 3x3 grid, then it has little o of n square edges. And in the joint work with Gish-Boliner, we disproved Elekesh conjecture, which I should mention. Elekesh conjecture was motivated by problems in discrete geometry. We didn't prove the Furedi-Rusinko conjecture, but we came close to it. And it's the construction is very simple, and it has a short, sleek proof, which I will not show, but let me just tell you what is the construction. So the construction has the vertex that has 3 copies of FP, which I will call X, Y, Z. And the edge set, what we take is that for every non-zero X and A in FP, we put an edge that contains the vertex X from X, X plus A from Y, and X times A from Z. And this suggests a natural approach for proving the lower bound for the 9-6 configuration. So to do this, it's enough to construct a linear 3 graph with the required number of edges and no grid and no 6-3 configuration. And we also observed that to do this, it's enough to find a subset of FP of size P to the n minus little of 1 with no solution to the quadratic equation A plus C square minus C equals B square in distinct A, B, C. So this is whether such a set X exists is an open problem. Okay, so let me now move to talk about variants of the regularity lemma. So let's first see how one derives the removal lemma from the regularity lemma. So I remind you what is the triangle removal lemma. He says that if a graph, you need to remove epsilon n square edges to destroy all triangles, then you contain delta n cube triangles. And the proof of the triangle removal lemma also uses the counting lemma. What does the counting lemma state? It states that if you have three vertices, V1, V2, V3, and the three bipartite graphs between these three clusters are dense, meaning they have density at least epsilon, and they are epsilon over 2 regular. So remember, this means that if you take any pair of subsets, let's say in V1 and V2, the density between them is very close to the density between V1 and V2, then the number of triangles between these three sets is large. It's polynomial in epsilon times n cubed. Okay, so let's see, how do we prove the removal lemma form using the regularity lemma and the counting lemma? So suppose we get a graph that is epsilon far from being triangle free. We apply the regularity lemma with, let's say, epsilon over 20. We get this partition. Remember, K is bounded by a function of epsilon. Then we do the cleaning process. We remove edges inside the clusters. We remove edges between Vi and Vj if there are few edges between Vi and Vj. And we remove edges between Vi and Vj if Vi and Vj are not epsilon regular. So it's easy to see that by doing so, we remove less than epsilon n square edges. And by the assumption, there is still a triangle remaining. Now, in this case, this triangle must belong, it has one vertex in 3 sets, such that the 3 sets are both dense and regular. So this means by the counting lemma that this triple of vertex sets contains lots of triangles. Now, what is lots of triangles? It's roughly n over k cubed. Now, luckily, k is just bounded by a function of epsilon, and therefore delta is at least 1 over m of epsilon. So this sounds like very good news, but what are the bad news? The bad news is that m of epsilon, Semeredi's proof of his theorem, showed that m of epsilon is bounded from above by a function of epsilon by a dreadful function of epsilon. It's 2 to the 2 to the 2 to the 2, 1 over epsilon many times. So therefore, what the above proof gives is that delta of epsilon, although it's a constant that depends only on epsilon, it's 1 over tower of height polynomial in 1 over epsilon. And actually, Ruja and Semeredi proved that delta of epsilon is not polynomial in 1 over epsilon. It is at most epsilon to the log 1 over epsilon. And interestingly, this comes from the lower bound for the 6-3 problem that I mentioned in the previous section of the lecture. So of course, at this point, one can ask, can we improve the bounds for delta of epsilon, meaning the bounds for the removal lemma, simply by improving the bounds for the regularity lemma, because we know that they are connected. But amazingly, Gowers proved that this is not the case, meaning that m of epsilon, the bounds for the regularity lemma, indeed grow like a tower of height polynomial in 1 over epsilon. But about 10 years ago, Fox managed to find a new proof of the removal lemma that avoids the regularity lemma and gives a bound which is tower of only of height logarithmic in 1 over epsilon instead polynomial in 1 over epsilon. Now it's worth mentioning that the recurring theme in extremal combinatorics is to try to design weak versions of the regularity lemma. What do we mean by weak? I mean that their guarantees are weaker than the guarantees of the full-fledged regularity lemma, but what we gain is that the bounds are much better. Instead of being tower, perhaps they are only exponential, and perhaps the best known example is the Fries-Cannon weak regularity lemma, that what it guarantees is that instead of guaranteeing a very good local control on the edge distribution, like in the regularity lemma, where you know the edge distribution between every pair of clusters, what you get is only global control on the edge distribution. What we gain is that the bound in this weak regularity lemma are only exponential instead of tower. And this is good enough. For example, if you want to approximate the max cut in the graph, then we only care about global edge distribution, and this is good enough. Another variant is the Duke-Leffman-Redel cylinder regularity lemma. In this case, the statement is more complicated, but roughly what we do, we cover the graph by 3-partite graphs or k-partite graphs, etc. In general, such that each of these k-partite graphs is regular, and this is good for other purposes. For example, if we want to approximate the number of induced copies of graphs in a big graph. And an interesting thing that happened is that we accidentally found another weak variant of the regularity lemma, which gives a new proof of Fox's result. And to get to this, I need to consider another problem, which is the hypergraph version of the removal lemma. So just another short definition is that I will denote by k r plus 1 r. This is the complete R graph on R plus 1 vertices. So we take R plus 1 vertices and all possible R plus 1 edges on these of size R on these R plus 1 vertices. So for example, K32 is just a triangle, right? It's the complete 2 graph on 3 vertices. And we have the following natural generalization of the triangle removal lemma to R graphs. And what it says is that if an R graph is epsilon far from being KR plus 1 free, meaning that you need to remove a positive proportion of the edges, then this R graph contains a positive proportion of all complete graphs on R plus 1 vertices. Now, this result was conjectured, this theorem was first conjectured by Erdős, Frankel, and Redel in the 80s. And the original motivation was to give a new proof of Semeredi's theorem about the fact that Rkn that I defined earlier is little O of n, and also as a way to prove the Brown-Erdős-Sós conjecture. Now, the main challenge in proving this, the removal lemma, is to find a regularity lemma for R graph that will use the correct notion of epsilon regularity. So I defined what is epsilon regularity for graphs, and we had this magical coincidence that this notion was useful and every graph had such a partition. Now, it turned out that for hypergraphs, it's very difficult to define what is this correct notion. Again, the idea is that we want a notion that will be strong enough to be useful. For example, that we could prove the R graph removal lemma using it, but weak enough so that every R graph has such a partition. So this was this was first achieved by Gowers and Redel, Skokan, Nagel, and Schacht. And all these proofs proceed by recursively applying the regularity lemmas for R-1 graphs and R-2 graph, etc. And therefore, all these proofs, they give Ackermann-type bounds for the R graph regularity lemma, and therefore also Ackermann-type bounds for the R graph removal lemma. And later, Tao gave another proof of the hypergraph regularity lemma and removal lemma, and he predicted two things. First of all, that it should be possible to obtain primitive recursive bounds for the R graph removal lemma, meaning that there is an absolute constant C that is independent of R, such that the bounds for the R graph removal lemma are in the fixed level of the Ackermann hierarchy. But on the other hand, that for the regularity lemma itself, we do need to pay the R bounds that are on the R level of the Ackermann hierarchy. And in a joint work with Moshkovitz, we confirmed this second prediction of Tao, meaning that there is an Ackermann-type lower bound for the R graph regularity lemma. And there are, as I've said, there are many variants of this regularity lemma, but our lower bound is actually holds for a very, very weak version of the hypergraph regularity lemma that is weaker than all of these variants. So therefore, it gives a lower bound for all of these variants. Now, it's a somewhat involved proof, but just a hint on what's going on there. So how did Gowers prove his lower bound for the graph regularity lemma? So his insight was to show that actually the process for producing a regular partition, as in Semeredi's proof, is unavoidable. And this process goes by starting from a partition and repeatedly refining this partition, each time paying an exponential payment. And because we do this 1 over epsilon many times, this series of exponentials gives you a Tau bound. And the main challenge with extending this to R graphs is that we need to allow an adversary to modify the graph. What do I mean by this? Is that the statement of the hypergraph regularity lemma involves not only partitioning the vertices, the vertex set of the hypergraph, but also a sequence of graphs that we construct or the adversary construct and help us in the definition of what it means for a hypergraph to be regular. And it turns out that to prove a lower bound, it's not enough to recursively apply a lower bound for graph regularity. We need to recursively apply a lower bound for a weaker version of the regularity lemma, meaning we need a stronger version of Gowers' lower bound where one is allowed to modify the input graph. So let me just give you what is the statement. The statement is that for every epsilon, there is a graph with epsilon n square edges, so that even if I allow you to modify this graph, add or delete epsilon n square over 100 edges, still every epsilon to the 10, let's say, regular partition of this new graph has towerly many parts. Now observe that if I allowed you to modify epsilon n square edges, you could just remove all the edges of the graph and have a regular partition of size 1. But if I allow you to modify just 1%, then you already need to pay this tower bound. And once we had this lower bound, we were wondering whether there is a matching upper bound, and we proved this matching upper bound, meaning that if a graph has epsilon n square edges and we get the freedom to modify 1% of its edges, then we can construct a very regular partition of this graph where the size of the partition is tower of height log 1 over epsilon instead of polynomial 1 over epsilon. And then we realized that actually this weak version of the regularity lemma is actually strong enough for proving the removal lemma. And how do you do it? Well, you just carefully redo the standard proof of the removal lemma using graph regularity. You apply this version of the regularity lemma, you modify it, you clean the graph, and you find these triangles. And since in the original proof, if you think about it, we already modified the graph, then these extra modifications that we do here, they don't cost us too much. Of course, you can ask me, but wait a minute, you are allowed to remove edges, but add also edges. So you might get triangles that didn't appear in the original graph. And then my answer will be that I just said that you needed to do it carefully. And this way you can avoid this. And of course, as I promised, this gives a new proof of Fox's bound for the regularity lemma, for the triangle removal lemma and the general removal lemma. Okay, so the last result related to hypergraph regularity lemma is related to a variant of Ramsay's theorem. So Ramsay's theorem is, of course, a huge area within extremal combinatorics. And the most famous result is Ramsay's theorem that says that every graph has a homogeneous set of size logarithmic in n, where a set of vertices are homogeneous if it's either complete or empty. Now, the upper bound, meaning the fact that there are graphs where the size of the largest homogeneous set is of size log n, is of course achieved by random graphs, as was shown by Erdős in the 40s. And the meta question in extremal combinatorics is the meta statement that graphs where the largest homogeneous set is of size order log n, they should be random in some way. They have many properties that we expect to find in random graphs. Now, one of the properties we expect to find in a random graph is that the fact that they should contain a copy of every fixed graph. Okay, so this motivated Erdős and Heinen to conjecture that if we assume that an n-vertex graph is induced H-free, where H is fixed and n tends to infinity, then we should be able to find a homogeneous set of size much larger than log n, of size polynomial in n. So this conjecture is still open, but you can also ask, so let's assume that our graph is, again, induced H-free, and we don't insist on getting a really homogeneous set, meaning either completely empty or completely full, but it's enough for us to have, let's say, at most 1% of the edges, or at least 99% of the edges. Then a theorem of Redel from the 80s, which was one of the first applications of the regularity lemma, is that in this case, remarkably, you can get a set of linear size. So again, so if your n-vertex graph is induced H-free, you can have an almost homogeneous set of size linear in n. Now you can ask, so what happens in hypergraphs? So unfortunately for hypergraphs, another major open problem is to determine the Ramsay function for 3 graphs. So we know that it's at most a square root of log n. And we also know that probably there is no analog of the Erdős-Heinel conjecture, meaning we don't gain anything by assuming that our graph is induced H-free, if we really insist on getting either a complete or empty set. But together with the Amir and Tiomkin, we asked what is the analog of Redel's theorem, and it turns out that the analog of Redel's theorem is that if a hypergraph is induced H-free, then you can find an almost homogeneous set of size logarithmic in n. And there is a matching lower and upper bound, and the proof uses the hypergraph regularity method, and there is a folklore conjecture that for larger R, the bound should be log n to the 1 over R minus 2. The lower bound, the upper bound is easy. The main thing is to prove the lower bound. And I should mention that already this is open already for R equals 4, and this is related to a famous problem of Nikiforov, which is to show that if you have a graph with many triangles, Cn cube triangles, then you have a large blow-up of a triangle, where by large I mean log n over log 1 over C. Okay, so let me move to the third part of the lectures where we discuss variants of the removal lemma. So again, I'm reminding you what is the removal lemma, and I'm stating it in a slightly different manner. Instead of that, if a graph is epsilon far from being triangle phi, then it contains n cubed over some function of epsilon many triangles. And now this removal of epsilon we think about as a large integer and not as a positive real. Okay, it will be useful, as you'll see in the next slide, to define it this way. So given this statement, there are many natural questions to ask. So for example, is this removal of epsilon, is it polynomial in epsilon? So we know that it is not. If it's not polynomial, how fast does it grow? Well, we don't know. We know that it's not polynomial, and we have these huge tower type upper bounds. And then we can ask, can this be extended to other properties? For which properties is it polynomial? Is there an example where this function is exactly exponential in 1 over epsilon? Is there an analog for hypergraphs? And can this be extended to other discrete settings, matrices, permutation, etc.? We will address some of these questions now. So let me say that the graph property is hereditary if it's closed under vertex removal, meaning that if a graph satisfies the property, if you remove a vertex, you still get a graph in the property. So most of the graph properties that you encounter in day-to-day life are hereditary, for example, being triangle-free, being three-callable, being planar, being interval, being perfect, etc. All these properties are hereditary. And in a joint work with Alon, we proved that every hereditary property has a removal lemma, meaning that for every hereditary property P, there is a function removal P of epsilon, so that if a graph G is epsilon far from P, then if you sample this many vertices, so this is just a quantity that depends on epsilon, many vertices, then with positive probability, let's say 2/3, you get the set of vertices that you sampled contains a graph that doesn't satisfy the property. So a corollary is that for every hereditary property P, there is a constant time algorithm that can distinguish between the case that the graph is in the property from the case that the graph is epsilon far from the property. And again, what is the algorithm? It just picks this many vertices at random and checks if they span a graph in the property. And what is the main tool that we used? So we previously discussed weak versions of the regularity lemma. So this proof uses a strong version of the regularity lemma that was obtained by Alon, Fisher, Krivelevich, and Szekedy. And I should mention that the alternative proof of this theorem using graph limits, which is another huge area of extremal combinatorics, somewhat parallel to what we are doing here, was obtained by Lovas and Szekedy. And then this result was extended to the setting of R graphs by Osting and Tao and by Reden and Schaft. Okay, so we know that for some properties, so I should mention that the bounds that we get here for this infinite removal lemma, of course, they are even worse than tower type. There are some, in general, this function might not even be recursive, but this is some not very interesting cases. But it's natural to ask for which hereditary properties can we obtain polynomial bounds for the removal lemma. So let me say that the hereditary property P is finite if P is equivalent to forbidden a finite number of induced subgraphs. Okay, so this hereditary property we are considering now as properties of the form we forbid, let's say, not containing induced copies of some 5 graphs or something like this. And I should mention that this characterization problem is already open even for finite properties. Now, in a joint work with Gish-Boliner, we proved a sufficient condition for a finite hereditary property to have polynomial removal lemma. And this has a very clean and simple sufficient condition. What it says is that if you have a finite hereditary properties, and there are three graphs not satisfied, not in the property, one of them bipartite, one of them co-bipartite, meaning a complement of a bipartite graph, and one of them split, meaning that you can partition the vertex set into a clique and an independent set, then this property has polynomial removal lemma. So for example, this applies to the property of being not containing an induced path of length 4, because you can convince yourself that the path of length 4 itself, it's bipartite, co-bipartite, and split, and therefore it has polynomial removal lemma. And this was actually a theorem of Alon and Fox that it had an ad hoc argument, and we get this immediately from this general theorem. And the key tool that we used in order to prove this result was a regularity lemma with polynomial bounds, not tower type bounds, but polynomial bounds, that is due to Alon, Fisher, and Newman. And what it addresses is the case where you have a graph that has few copies, induced copies of some fixed bipartite graph. So given this sufficient condition in this theorem, it's natural to ask whether there is a matching necessary condition. So unfortunately, we don't have a matching, but we have a nearly matching necessary condition, which is that if you have a finite property that has polynomial removal lemma, then there should be a bipartite and co-bipartite graph not in P. So it's nice to observe that these two necessary and sufficient conditions, they can be used to prove essentially all the positive and negative results that were previously proved regarding this problem. Now, continuing with this theme is that Alon also conjectured that every semi-algebraic graph property has a removal lemma with polynomial bounds. Now, I will not define what are semi-algebraic graph properties, but I will just mention that an important subclass of these properties are what is called geometric intersection graph properties. So, for example, you can say that a graph is an intersection of unit balls in R3 if you can assign to each vertex a unit ball in R3, such that UV is an edge if and only if the ball of V and the ball of U have a non-empty intersection. And so semi-algebraic properties are the natural generalization of this property to not necessarily in R3, not necessarily unit balls, etc., etc. Okay, but and what is the motivation? The motivation is that many extremal problems, for example, Ramsay's theorem or Turán problem, they become much easier if we assume that our graph is semi-algebraic. But it's important to note here that we're not assuming that our input is semi-algebraic, but that the property that we are studying is semi-algebraic. And with the Gish-Boliner, we proved that Alon conjecture is indeed true. And this was done by using some of the methods used to prove the result in the previous slide, together with some other ideas that are specific to the family of semi-algebraic properties. Note that semi-algebraic properties are not finite. They cannot be characterized by a finite number of forbidden subgraphs. So let me discuss now another problem related to this general characterization problem, is that now we fix an R graph H and we call P sub H the property of not containing a copy of H. And the very influential result of Alon is that if you look at the property of being H free, then it has a polynomial removal lemma if and only if H is bipartite. And this result was the starting of many many results in this area in the last 20 years. And 2 years later, Hayakawa, Nagel, and Redel, they conjecture that the natural generalization of Alon result holds also for R graphs, meaning that the property of being H free in R graphs has polynomial removal lemma if and only if H is R partite. Now I should point that the if part is easy, because if a graph has epsilon n square edges, and H is bipartite, then it's easy to see that it has poly epsilon times n to the h copies of h, where little h is the size of h. And the same holds for R graphs using a theorem of Erdős from the 60s. What is hard is the only if part, meaning to show that if h is not R-partite, then the removal lemma is not polynomial. So this was done by Ruja and Semeredy when h is a triangle. And what Alon did is to extend the Ruja-Semeredy proof to arbitrary non-bipartite graphs h. Koyakawa, Nagel, and Redel extended Ruja-Semeredy from triangles to complete R graphs on R+1 vertices. And in a joint work with Noga from 2005, I think, we managed to address some of the non-R-partite R graphs. And the full conjecture was resolved recently in a joint work with Gishboliner. And let me quickly go over them like a nugget from this proof. So again, the thing is that we need to show that if an R graph is not R-partite, then its accompanying removal lemma is not polynomial. And the main idea is to look at the two shadow of H. So again, H is an R graph. Every edge is of size R. And we define S, so this is a graph, to be the two shadow of H. So this is a graph. Its vertex set is the same vertex set as H. And UV is an edge in S if U and V belong to one of the edges of H. Okay? And now, the first lemma that we prove is that if S, the two shadow of H, if it has an induced cycle of length at least 4, then we have a lower bound. Then the removal lemma is not polynomial. And to do this, we extend Alon's proof for graphs. The second lemma handles the case when the shadow of H has a clique of size R+1. And to do this, we extend the Kohayakawa-Nagel-Redel proof for complete R graph on R+1 vertices. And now let's see why these two lemmas allow us to handle all possible non-R-partite R graphs. So first of all, by lemma 1, we can assume that S has no induced cycle of length at least 4, because if it has, then lemma 1 gives the lower bound. So we can assume that S has no induced cycle, and therefore S what is called chordal. This is exactly what chordal graphs are, and it's well known that chordal graphs are perfect graphs, where I remind you that perfect graphs have the property that they have the same chromatic number and the same clique number. Now, the assumption is that H is not R-partite, and if H is not R-partite, then its two shadow is not R-callable. It's not an R-callable graph. And since we know that it's perfect, it has an R+1 clique, and if it has an R+1 clique, then we can use lemma 2. And this more or less covers all the cases. Not more or less covers all the cases. Okay. So we've seen that there are some properties for which the removal lemma is polynomial bounds, and there are some cases where the bounds are not polynomial, but there is a huge gap between the lower bound and the upper bound, for example, being triangle free. So Goldreich asked, is there a property for which the removal lemma is exponential in 1 over epsilon? Exactly. And together with Gishboliner, we proved that this is indeed the case. We in fact proved that for every super polynomial function f, there is a property whose removal lemma is exactly f of theta of epsilon. And actually, the property is very simple. You start from the cycle of length 3, and then you repeatedly apply the function f, and the property is not containing a cycle of any of these lengths. And the nice feature of this proof is that it allows us to resolve another problem mentioned in the paper of myself in Alon, is that we ask for which odd cycle length, forbidden odd cycle length, the removal lemma is polynomial in 1 over epsilon. So we know that if we forbid all odd cycle length, meaning this is just 2 callability, the bounds are polynomial. And what we proved is that if the integer ai forbidden is 2 to the 2 to the order of I, then the bounds are polynomial. And if it's much more than this, then it's not polynomial. And to prove this result, so this is the last result I'm going to mention, to prove this result, we consider what is called the generalized Turán problem. So a Turán problem, we fix a graph H and we ask, what is the maximum number of edges in a graph on n vertices without a copy of H? And the generalized Turán problem is that we fix two graphs, H and T, and we ask what is the maximum number of copies of T in an n-vertex graph without copy of H. And it's easy to see that this is indeed a generalization of Turán problem. And it's also amusing to observe that actually the 6-3 problem that I mentioned at the beginning of the lecture is just another special case where T is a triangle and H is the diamond graph. So this generalized Turán problem has been studied extensively in the literature, and to prove the results from the previous lecture, so together with Gish-Boliner, what we proved is the type bound for the generalized Turán problem of every pair of odd cycles. Okay, so this is all the time that I have. You can find a much more detailed discussion in my survey paper in the proceedings. And let me thank you for your attention.
Okay, thank you, Asaf, for a beautiful lecture. It's a shame that there's no possibility to ask questions on this platform. So just thank you very much.